processes make it somewhat challenging for us to get to mass balance from ICET2 or any other altimeter out there. Okay, so starting at the ground level here, ice sheets are the largest store of freshwater on the planet. We know this, and the Antarctic ice sheet is the largest by far. It's also my favorite ice sheet, in case you can't tell by the end of this talk. And so we really want to understand how these ice sheets are changing, because they ultimately have such a mass of water that can ultimately largely change sea level. So the Antarctic ice sheet consists of grounded ice, which is the interior ice sheet that's actually sitting on bedrock underneath it. And then that ice actually flows out into portions called ice shelves that are floating ice. And this is really sort of the Antarctic system. It's interacting with the atmosphere, it's interacting with the ocean. And we want to understand how this entire ice system is evolving in order to understand ultimately what the sea level contribution from this ice sheet would be. And my cat will probably make multiple appearances here, so please forgive me for that. I always like to show this, whether it's to the public or to remind other scientists just how large the Antarctic ice sheet is. It's about almost two times the size of the contiguous United States. And what this means is it's a very complicated area. It has largely different climates depending on where you go, just like, the weather in Scripps doesn't look like the weather in New York City. So it's a very large area. It's challenging to measure. It's remote, and it has a lot of ice stored in it. And unfortunately, it's not just a static ice cube, as we all know. There's lots of fluxes across interfaces. We have, starting in the interior of the ice sheet, we have snow accumulation, sublimation, redistribution. Then that accumulation acts to drive ice flow. The ice becomes buoyant at the edges and creates shelves, and then it interacts with the ocean. And so there's just lots of different pieces to this puzzle. And this is really what's controlling the mass balance of the ice sheet and ultimately sea level. So to understand sea level, we need to understand the ice sheet mass balance. And so this is quite simply, is it getting bigger? Is it shrinking? Or is it in somewhat of a state of balance where there's no change occurring? And the simplest look at this is, if mass input outweighs mass output, then your ice sheet is growing. And what are the drivers of mass input and output? Well, we have snow accumulation. That is the input into the system. And then for output, we have iceberg calving, basal ice shelf melt, and surface runoff. And as we're all aware, if you take the difference between these two, this really gives you your mass balance, and that residual is sort of what we expect to be entering the ocean, giving us our understanding of sea level. So for this talk, I'm going to ignore the mass output. Obviously, it's extremely important, and it's quite a large number, but I want to talk specifically to the mass input, because this is quite a large number, and it can play quite the role in mitigating sea level rise. So to kind of come back to my little Antarctica map with the United States on it, snowfall over the grounded Antarctic ice sheet is pretty small. If you average it across the entire ice sheet, it's about 170 millimeters of water per year, which is about 7 inches. So if that's kind of averaged across the whole ice sheet. And so it's really a desert. It doesn't get that much accumulation unless you're near the periphery. So one might think, well, then does it really matter that much? In fact, it does. So, I put here little things make big things happen. So when you have a very small number, but you're integrating it over a very, very large area, it becomes something of great significance. So the amount of snow that falls actually every year over the Antarctic ice sheet is equivalent to about 6 millimeters of sea level. So there's a lot of water being stored in the ice sheet in the form of snow accumulation, and it's highly variable in time. And so any changes to that number can actually impart significant changes in sea level. And so I just wanted, for reference here, I grabbed the latest chart from sealevel.nasa.gov that, you know, we're currently at 3.3 millimeters per year. And so you might imagine as if we start to enter these different states of snow accumulation for the ice sheet, we can start to really change that number. Okay, so that was like my very basic level, making sure everyone's on the same page introduction. Now I'm going to kind of dive into some of maybe the drivers of, or some of the topics that kind of drive my interest, and then get a bit more into the science as well. So I have past, present, and future here. And of course, just to be complicated, I'll start in reverse order and speak to the future, because ultimately that's really what drives most of, at least my science, is trying to help us understand into the future how things will change and what it means for society into the future. So it's sort of my benchmark as to what I'm looking for when I do my research today. So again, very basically, this is something that I think everybody has been told at some point in their careers, is that, you know, in the future, in a warmer world, we expect more snow accumulation over Antarctica. You get warmer temperatures, you can keep more moisture in the air, and then you can precipitate more. And so that's kind of the blanket statement that I think everyone understands about the Antarctic ice sheet going into the future. And there was this great paper a few years ago that showed that this is indeed what a variety of climate models indicated. So you don't have to obviously understand each of these individual models, but the gist of it is that, you know, you get warmer temperatures and then you get more snow accumulation. And these plots look very convincing, and they're very linear, and it looks like you can almost easily predict into the future what the change in snowfall will be given a specific change in temperature. So the question is, in a warmer world, then will snowfall help mitigate sea level rise? And I might argue it's a bit more complicated than just that statement alone. And so there's another paper that show that it's actually not quite clear, given the current state of climate models, what the impact of future snowfall will be on mitigating sea level. And so this is just looking at a handful of different, I believe, CMIP-5 models over different RCP scenarios, and looking at what they predict the contribution from sea level to be, the contribution from snowfall on sea level rise. And so if it's above 0, that means it predicts there will be less snowfall and in fact actually cause sea level to rise. And then if it's below 0, then it means that it's predicting more snowfall and there will be sea level fall. But you can see there's a large range between the different models in the actual, sometimes sign and even magnitude of the change. So it's not necessarily cut and dry of what the role of snow accumulation will be on future sea level change. And so, yeah. And we have to remember there are other drivers of accumulation change, of snowfall variability, and that it's not just a thermodynamic process, that there's actually atmospheric circulation that can, changes in atmospheric circulation can also play an important role. And for instance, the belt of the westerlies that encircle the continent can change in strength and position, which then could impart changes in snowfall as well, because you might imagine your storm systems will have different trajectories based on this, and the strength of them can vary as well. So it's something that always interests me, that is it purely this, when it gets warmer, it gets wetter, or are there added additional complexities to the problem that might not be so simple as as you get warmer, you get more snowfall. So back to my question once more. Well, actually, I put maybe, and I think the answer is yes, but it's not as clear cut as a simple increase in snowfall due to temperature. There's going to be additional changes that will impart different signals on the snow accumulation changes as we go into the future. So let's see. So I might say now let's think to the present day. So if we've sort of looked to the future, said we need to understand future changes in snow accumulation to better project what Antarctica's contribution to sea level rise would be. But are there present day analogs or present day scenarios that might help us better understand what we might expect into the future? And this is where we're fortunate, excuse me, that we have, you know, a handful of models at our disposal. And I have a completely non-exhaustive list here, but some of the major players that I'm sure many of you have used, and myself included, where we have atmospheric reanalyses that assimilate observations. So the ECMWF ERA interim, ERA 5, and then NASA's MERA 2, which is one that I use quite frequently. And then we also have regional climate models, and both these RACMO and MAR are both forced by ERA interim. So we have these fantastic data sets, and what's wonderful about the global models is it really helps us to add context to the observed changes that we're seeing. So that will be something I hope that I can kind of touch on in a minute. So if we just say, let's step back and what's happening in to snow accumulation over Antarctica in the different models. And so what I'm showing here is the trend in annual P minus E, which should effectively represent net snow accumulation for the different models. So the top row, I sort of bunched together because they are the reanalysis products, and then the bottom two, MAR and RACMO, are regional climate models. And if you kind of squint your eyes, you might think, okay, they kind of show the general same pattern here. And so you might have, say Drawing Maudland, you have increased accumulation rates, and then perhaps in Wilkes Land, there's decreases. So if you kind of, in general, I think they show somewhat correspondence here. But if you instead take each of those models and stack them, those trends within the models, and stack them on one another, and you say, give me the minimum trend and the maximum trend, you can see you can kind of get whatever trend you might want to, depending on which model you use. So you almost entirely everywhere can get a negative trend, or you can almost entirely everywhere get a positive trend, depending on which model you use. There are some exceptions, obviously, but the point is more that there's still not consensus between these models, and it's really not surprising. I'm not trying to be shocking here, because we all know that especially for reanalyses, they struggle because they do assimilate data, and they're very strongly influenced by an evolving observing system. So if you have satellites coming online or going offline, it can generate a really spurious jump in different variables that really makes trend analysis difficult trend analysis is just challenging with reanalyses, and there is no perfect model, and no model is really better or worse than another, and so we have to keep them all in mind in thinking of what is a realistic portrayal of the Earth's system at this time, and so we really need observations to help us. And I use the word, I put the ground truth in quotes here because I'm not exactly sure if ground truth is the right word here, but we need some way that we can start to use observations to help us understand the challenges that each of these models are encountering in basically in assessing some of these variables. So at the same time, I'm being a little bit challenging to the reanalyses, but at the same time, they're extremely, extremely valuable because they're global models that are assimilated into an entire framework that allows us to not only look at change, like I can map the trend in P minus C, but we can also look at the drivers of change. So they're extremely, extremely valuable. And then my final statement here is, the satellite era is really just too short at this point. I mean, we know that the variability in snow accumulation is extremely high on a year-to-year basis. And so it really makes it beyond difficult to try to make any sense of how the snow accumulation is changing over the ice sheets when we just don't have enough time to pick out the trend over the noise. And we saw this a bit with some other work looking at air temperature. So a similar concept being on the bottom row, this is temperature trends from the different reanalysis models. These are, I think, well, yeah, this is Mara. So this is sort of the previous generation of analysis. But on the top is actually when you take observations, so actual AWS stations, and basically reconstruct them across the entire ice sheet. And then you can see for the reconstructions, no matter which sort of model you choose to help guide your reconstruction, you get about the same result, whereas the individual reanalysis models all have widely different trends. And so the idea being that what can we, if we can't necessarily trust the trends in the reanalyses, what can we use them for to help us better evaluate observations? And hopefully I'll get to what I mean by that in a moment here. And this is almost more of a side note or a digression, is that one of the things that I always kind of struck me was there's two fantastic papers came out in the 2000s by Andy Monahan and Eric Steig, and the first being that there hasn't been a significant change in snowfall since the IGY, which was 1957. And then the second being there was warming of the Antarctic ice sheet since the IGY. And so does that mean, is that at odds with our initial perspective that in a warmer Antarctica, then we should get more snowfall? And there's lots of caveats behind that, but it was just sort of this interesting sort of portrayal of these two different variables and how their titles are very similar, except minus the insignificant part. So this kind of motivated me to look more into how we can maybe start to understand what's truly driving Antarctic snow accumulation. And so now I'm going to look to the past. Can we use trustworthy observations of ice cores to actually, basically with a fusion with the reanalysis models to get a best guess of what sort of historical snowfall might have looked like? And so why would you look to the past? Well, one is to ensure that if there's any trends in the snow accumulation, that they're observable over the noise. You also want to understand the direct impact of snow accumulation on observed sea level change. What is it actually doing? Is it gaining mass? Is it losing mass? And what does that mean for sea level? I thought another important thing is to also have an observation-based data set that we can then go to global and regional climate models and help us better evaluate them. Are some struggling in some regions and doing better, and why is that? Can we go back and understand what that reason is? And then finally, obviously, to understand the drivers of accumulation change. So this work is now a couple years old, but I wanted to quickly touch on it in that basically we tried to take the best of both worlds here, right? Where we have ice core observations that are actual field observations. They can go back several, I mean, the ones I'm using only go back several centuries, but obviously you can imagine much deeper and longer term ice cores exist as well. The cons there, the map on the left, there's just not that many. And then they can be noisy. They can have lots of small scale variability from wind redistribution, et cetera. And then you have your atmospheric reanalysis, which is spatiotemporally complete, but only from, the satellite era to present day. And then, as I already mentioned, the trends are often unreliable. And so the gist of it is that we're really taking the spatial patterns within the reanalysis to help us sort of better interpolate these different ice core records to get a complete look at snowfall over the ice sheet. And we used 52 Fern and ice cores from across Antarctica that are shown here. And what this map is basically showing you is where you can expect the reconstruction to do a good job and where you can expect it to not do as good of a job. So if you're in the greens, that means that accumulation record is strongly correlated with the reanalysis. And then as you get into the yellows and the pinks, it's not as good. And as you can tell, it's pretty much a proximity thing. The closer it is, the closer a grid cell is to a core, the better the correlation. So you can see it's not perfect by any means, but we hope that we were able to at least propagate uncertainty enough to ensure that even in those regions of pinks, that we're at least acknowledging that it's not perfect. And you can think of it, that's sort of the spatial distribution, but you can also think of the temporal distribution as well. This is the number of cores through time. So sort of the maximum that we get is in this sweet spot between the mid 50s to the mid 90s. And then you can see a rapid drop off into modern day. And then going further into the past as the records drop out, then you get fewer and fewer. And so the fewest for any given year is 29 ice cores. And what we find is that these are the actual trends we end up with in snow accumulation. The top one being for over the past century, and then the bottom one being since the IGY, is that it's not a homogeneous signal. There's lots of spatial structure here. And you see regions of strong decreases and strong increases. And the clearest pattern you see is this seesaw between the peninsula and eastern West Antarctica and the Ross side of West Antarctica. But East Antarctica also has very interesting alternating gains and losses as well. And there's way too much on this slide, but if we just focus, say, on the upper left, that's integrating that the whole, my whole reconstruction over the entirety of the grounded ice sheet. And it shows that there was an increase in snow accumulation that has been slowing down recently, that largely being driven by East Antarctica. West Antarctica doesn't really do too much. Whoa. And then the peninsula, I have no idea what's happening here. Sorry about that. My mouse is going crazy. All right.
Can I just take this moment to ask people if you could please mute? Every so often I hear bits and bobs of
other people. For some reason, I'm having difficulty muting people.
Sorry about that. So is it, are we having the same problem before, or is it all good?
You appear to be showing your notes again, so same thing.
Okay. Are we good now?
Yeah.
All right.
That's good.
Apologies about that. That was very bizarre. Okay, so the West Antarctic Ice Sheet is basically not really doing too much, and the peninsula is undergoing this unbelievably strong increase in snow accumulation, basically since the early 1900s. And what does this mean in the grand scheme of things? It means that actually snow accumulation was mitigating sea level about 1 millimeter per decade over the 1900s, and it appears to have accelerated since the satellite era. And you can see the breakdown on the right, where the East Antarctic Ice Sheet makes up the majority of this contribution, and West Antarctica makes up a small portion, and the peninsula is almost negligible. However, it's really what's responsible for this acceleration, in that it's receiving a significant amount of snow accumulation over the past 50 years. And one of the questions was, so what's driving this change? And so if you look at the trend on the left, those are actual trends from the reconstruction between 1957 and 2000. On the right is what would be the expected trend in snow accumulation due to changes in a shift in the index of the southern annular mode. So basically, you can regress a change in the SAM index against changes in P minus E, and then you can predict what the expected impact of a certain shift in the index would be on accumulation rates. And you can see they looked very similar, and about 80% of the spatial variability in the trends are explained by perhaps the changing westerlies. And so I thought after this, it's like, okay, that tells the whole story. It's the shifting of the westerlies that is likely behind this pattern of snow accumulation. But if you look even further, it actually cannot be the driver behind the increase that we saw in snow accumulation. It actually, this pattern on the right here actually results in a reduction in snow accumulation at the ice sheet scale. Whereas in the reconstruction, we found an increase in accumulation. So it actually is likely driving the small scale patterns, or I should more say regional patterns in the trends, but perhaps is not actually driving the changes that we observe. And so if you take the difference in those two maps, if you say, okay, I have my trend map, and then what I expect the impact of the southern annular mode would be, and that this is sort of the residuals that you get. And so it turns out that you could potentially account for these residual trends with various levels of warming, and those numbers are actually somewhat realistic for each of those different sectors of the ice sheet. So we couldn't necessarily make a mechanistic link between the two, but we couldn't necessarily say it couldn't be a warming atmosphere as well. We can only say that they're in line with one another. Some other new work suggests that there could be a link with ozone depletion. So in an ozone depleted atmosphere, they found that there was enhanced snow accumulation using a CSM model ensemble. But again, there was difficulty in actually determining what the actual mechanistic link was between the two. So to kind of summarize that section, 20th century accumulation, we found that it did increase and likely mitigated sea level rise. The atmospheric circulation changes likely are what dominate the spatial pattern of change, but the root cause of the overall increase is likely still unknown, but we cannot rule out things like temperature or ozone depletion. Modern day accumulation is about 80 gigatons per year higher than the 19th century. And however, my caveat at the end is about 70% of those century-long gains from snow accumulation have been offset by just 26 years of mass loss. So snow accumulation is doing its job, I guess, as best it can to help mitigate sea level rise, but in reality, the ice loss is just too strong, and snow accumulation is not keeping pace. Okay, so I want to quickly sort of switch gears a bit and talk about, so that's sort of thinking about the direct impact of snow accumulation and what it means for sea level rise and looking at past, present, and future. But now I want to talk about some of the challenges that snow accumulation and firn processes make for our interpretation of altimetry measurements and what it means for mass change and ultimately sea level contribution. So here's ICET-2 on the launch pad at Vandenberg in 2018. ICET-2 is NASA's next generation laser altimeter. And so its mission, for those who aren't aware, is to actually measure changing ice sheet height to a precision of better than 4 millimeters per year. So we are going to be measuring surface height, and we're going to be doing it to an extremely precise level. Okay. So here's a nice little cartoon of what exactly the beam setup looks like on ICET-2. It's not just a single beam. We have actually 6 beams, and they're arranged in 3 beam pairs. So each of those beam pairs are only 90 meters apart. That helps us measure surface slope. And then the 3 beam pairs are about 3 kilometers separation. So this really helps give us better spatial coverage. And I think maybe what's more interesting for what I'm going to talk about today is ICET-2 has a 91-day repeat cycle. And so, and that was on purpose because there is a goal to actually calculate height change seasonally and potentially even mass change seasonally. But I will talk a bit about what that means. So what you can do with ICET-2 is you can make beautiful maps of elevation change like this. And so this is actually crossover analysis between ICET-2 and its predecessor, ICESat. But I did want to note here in this group that ATL-15, which is one of the ICET-2 data products, will provide gridded height change over both Greenland and Antarctica. And that should be actually coming out pretty soon. So if you're interested in all this stuff, we're trying to make it as easy for everyone to get their hands on it as possible. So we make this beautiful map of height change, which can tell us about the volume change of the ice sheet, but not all of these changes really reflect the density of ice. The ice sheet is not a solid brick of ice. And so we have to get more creative in trying to understand what's actually changing here and what's the appropriate material density. So we have to partition the height change. And as I write here, ice sheet mass balance is really the combination of snow accumulation and ice dynamic changes. These are the height signals that we need to isolate from the non-ice mass related changes. So there's lots of things changing, and we need to figure out how to isolate those. And I'm going to step you through this here. So here's my schematic of an ice sheet. It's definitely not to scale, but we have bedrock at the bottom with ice on top of it, and then a fern column sitting on top of it. And fern is simply snow that has fallen and is getting buried with subsequent snowfalls and slowly changing from the density of snow into the density of ice. So height change is the combination of several things. So we have surface processes like snow, rain, sublimation, runoff, those actually impart a mass change. Then we have firn processes that don't impart a mass change, like firn compaction and meltwater infiltration and refreezing. And so this can generate a height change without actually resulting in a mass change. We have ice dynamics as well, which is, again, a change in mass, in ice mass. And then we have solid earth processes, which again, does not have a mass change, an ice mass change, I should say. And so ICET 2 actually, what it sees is the sum of all these things. It doesn't see one individual process. And so we have to disentangle it. We can get surface mass change from an atmospheric model. We can talk about how good that is separately, but ideally you can. And so often what is done is isolating. We want to isolate what the height change due to ice dynamics is. And so if we rearrange this equation, then you basically say, okay, we've got to take what ICET 2 sees and then subtract out all these other processes. We can use a GIA model to get at the height change of the solid earth. And then what I'm going to talk about is using the community Fern model and MERA 2 to actually account for surface processes and Fern height change. And for those of you who don't know, MERA 2 is a global reanalysis product that is produced at Goddard in GMAO. So looking just to the top, to the Fern part, as I said, we basically need to determine the height change of the Fern column by modeling surface and Fern processes. And so I'm kind of probably keep repeating myself a bit, but I think it's important, is that the surface processes involve ice mass, and we call this a surface mass balance. The Fern processes are air. They're just impacting air. There is no mass change occurring. And so we call this the Fern air content. And these are all a function of snowfall, rain, sublimation, melt, infiltration, refreezing. The temperature obviously controls compaction rates. And we take all of this information from MERA 2 and then you model all the changes in the surface mass balance and Fern air content. And so I guess I'm saying here, okay, say we've checked those boxes. We can say use something like ATL 15, but also insert your favorite flavor of satellite altimetry data in there. There's no difference. And then you can get your residual height change due to ice dynamics. And it's a simple conversion, right? Once you know you've isolated the component from ice, you know it scales to the density of ice, and you can get your dynamic mass change, and then you can get your surface mass balance from your model, and then you get total mass change. Super easy, right? And so to just recap that, surface height change is a function of several processes, both ice mass and non-ice mass related. Isolation of this ice dynamic signal requires corrections from GIA and also surface processes. And then mass balance is ultimately the sum of those ice dynamical and surface mass balance components. So now that I've oriented you to the Fern modeling effort and why we need to do it, I'll speak to how we actually executed it and what does this mean for sea level rise. So we use MERA 2, as I said. It's pretty coarsely resolved, about 1/2 degree latitude and longitude. And it covers the time period from January 1980 to present. And we actually run the model at 5 daily resolution. And we use several variables: snowfall, precipitation, evaporation, skin to meter air temperature. But what we actually do is we combine the coarsely resolved MERA 2 data with an offline MERA 2 replay that is run at 12.5 kilometer resolution. So I'll flip back and forth here in the map. You can see this is the annual P minus E between MERA 2 here and the M2R12K. And so you can see it can much better resolve lots of the complexity, especially around, say, the transantarctics and things like that. So we combine MERA2 with this replay. Unfortunately, the replay was only for 15 years. So really the final hybrid product is just the seasonal cycle from the high resolution replay combined with the residuals from MERA2. So it's kind of a mashup of the two together. One major challenge we ran into was that MERA2 accounts for meltwater processes, but actually only outputs surface runoff, and melt is not retained. And so we had to basically make a very simplistic assumption about melt fluxes, and we just used a degree day approach. And so we use the Trussell QSCAT fluxes to actually calibrate a degree day model for Antarctica. That the time series is shown above. I plot up, well, in yellow is the Trussell data, but then in blue, I plot up RACMO too. So it's a super simple assumption, but it seemingly does at least a good enough job for now, and we're working on ways to make it better. Okay, so that's the forcing. Then we actually use the community Fern model, which anyone can go out and grab. It's on GitHub. It's a one-dimensional Lagrangian model that basically models the evolution of Fern properties through time. And so at the end, you get this sort of depth, age, density, temperature, liquid water content product that shows how those variables vary in time for your given location. And you can also get things like runoff and refreeze and whatnot. So this is the modeling framework. I'm not going to go into it, but one of the other big problems that we run into is our understanding of what is the surface density, what is an initial density, and it's unfortunately just not well resolved. And so we just basically use the observations to help build a simple static model. So the black circles are where we have observations of the surface density. And then we used MERA2 to predict these surface densities. And so we end up with a median around 380 kilograms per cubic meter. And you can see the map shows you the spatial distribution. But again, and I think I come back to this, it's very, very much an unknown that can greatly change our results. So more to be done there for sure. So if you run your forcing through the community Fern model, you can end up with looking at the total Fern air content, which is the integrated air content within a column of Fern. And so this is typically in meters of air. So the map on the right shows you that, in the very dry, cold interior, you have very, very thick air content, which means you have a very, very thick Fern column. And then as you get into some of the warmer regions, you have less air. And then here's the same plot with just the mean SMB. The sort of median value across the ice sheet is about 0.2 meters of ice equivalent per year, but typical range from about 4 centimeters to 74 centimeters. And I write here that the integrated over the entire ice sheet, I don't know why I put mu there because that's not what I meant. But anyway, so integrated over the whole ice sheet, you have about 2,600 gigatons of snow accumulating every year. And then the interannual variability expressed as a standard deviation is 147 gigatons per year. So this is really where I wanted to get to. So hopefully I'm not running too late. I have no idea what time it is, so I apologize. So the question becomes, when we look at altimetry, we want to know how is the surface height of the ice sheet responding to variations in SMB and also the Fern air content. And what I'm plotting here is integrated over the entire ice sheet. And the blue line is the integrated height change or volume change from the surface mass balance in blue, and then from the Fern air content in green. And so the biggest thing I wanted to point out was that there's a very, very, very strong seasonality to these signals. And these seasonal variations outweigh the longer term trends. And so if you're trying to look at all at short time scales, the signal is completely dominated by surface processes, but in particular, not even just surface processes, the Fern air processes, which are completely unrelated to actual mass change. So if you're trying to look at volume change at the seasonal time scale, you really must be careful in accounting for the air content within the changes in the air content within your ice sheet, because it completely dominates the signal. So this really is going to make it challenging as we try to go to shorter and shorter timescales of understanding ice sheet mass balance. So that was just more something I wanted to point out. So to wrap it up and put it into perspective, in our most recent paper, in over a 16-year interval, we found that volume change over the Antarctic was 111 cubic kilometers per year. But the seasonal volume change can be basically an order of magnitude larger than that. So it's just to point out that as we go to shorter timescales, the surface processes become much, much more important. Yeah, and uncertainties in the surface forcing and Fern air content are what's limiting our ability to constrain mass balance estimates. But I would say the Fern modeling and understanding of surface processes is a very open field right now. There's just so many uncertainties that need to be ironed out. And I think the first one is really important, that uncertainties in the SMB forcing are amplified because, for instance, snow accumulation adds ice mass, but it also adds air. And so if there's any uncertainty in your snow accumulation, it's doubly included. And so it becomes further amplified, as I mentioned in the second bullet, by the lack of constraint on the density of that freshly fallen snow. And so any uncertainty in that gets propagated as well. We don't understand meltwater at all. That's a big unknown. Fern also has a memory. It's not only responding to forcing that happened in 1980, but it's still responding to this day. And then there's lots and lots more I can tell you about the challenges in Fern modeling. So to wrap up, climate projections vary in sign and magnitude of the Antarctic snow accumulation impact on sea level. They suggest warmer temperatures, more accumulation. Observations suggest that atmospheric dynamics are important, but also so is temperature likely. And so we did find that there was likely mitigation of sea level rise by additional snow accumulation. And finally, I think the biggest thing is we have to start to understand the biases in accumulation magnitude and trends, and what their limitations are for use over Antarctica, especially now in reference to things like modeling surface processes and interpreting satellite data, especially as we want to go to shorter and shorter timescales. So with that, I will end and take questions. I have no idea if I went way too long or not, so apologies.
Thank you very much, Brooke. That was really interesting talk. We're doing okay for time. Some of us have to go in about 20 minutes or so for another meeting. But we've got a little time here now for questions. So there are some questions here in the chat. There's a question here from, I'm just going to read them start to finish. So Vivian asks, what is the average time needed for moving from Fern to ice?
What is the average time needed to move from Fern into ice? Is that?
Yes.
Yeah, so it's a great question, and it actually varies. So some places, depending on the climate conditions, so if it's warmer, it's more rapidly compacted and can be just a few decades, to other places like in the middle of East Antarctica, where the Fern column is like 200 or 300 meters thick and the accumulation rate is only a few centimeters. It can take thousands of years. So when we spin up our Fern model, we actually have to take that into account, where we have to spin up our Fern model and build up a Fern layer, and it just can completely vary between just 100 or 200 years or all the way up to 10,000 years. So it's a function of the climate conditions that it experiences.
And then the next question is from Matteo. Are you still with us? Is there any chance you'd like to unmute, Matteo? I think it's nice to hear other people. You'd like to ask a question? Sorry to pick on you.
Well, I can see his question. So
Yeah.
So basically, how do we go from the hybrid approach, or how do we increase the resolution using the hybrid approach? So what we do is we have the full 12.5 kilometer offline replay of Mera 2, but it only spans from the year 2000 to 2015. And so we really need, especially because we're doing Fern modeling effort, we really need to have the longest record as possible. So we want to use the full Mera 2 time window, which is from 1980 to present day. And so what we do is basically take the 12.5 kilometer resolution replay and get the seasonal cycle over that 2000 to 2014 period for each of the 12.5 kilometer grid cells. And then we take the Mera 2 data over that same time window, get the seasonal cycle, remove that seasonal cycle from the Mera 2 data. So you have like a residual, and then you add that residual back onto the higher resolution hybrid data. So the temporal variability will largely be driven by Mera 2, and that won't have increased resolution, but where we wanted the increased resolution was to make sure that the magnitudes of, say, accumulation or temperature were better than if we just used the coarsely resolved Mera 2 grid. I think that should answer.
Yeah, thank you very much. That will help one of my interns who's also listening to this. Sorry, Craig, your voice was coming through all broken up to me, so I don't know. Perhaps you asked if I could read the question. Well, I guess anyway, Brooke answered, so thank you.
Mm-hmm.
Thank you. It's good to hear from you. We've got a question from Gavin. It's a bit of a statement, a bit of an argument. So increased interior precipitation is driven by the converging flux of water vapor moving southward. And so perhaps the atmospheric temperatures at 60 degrees south are important for this, and not necessarily the Antarctic surface temperatures.
Yeah, I think that's an excellent point. We took a very simplistic approach to just looking at temperature sensitivities across the ice sheet, but in reality, this is 100% correct. So it would be interesting if you know, there could be ways to relate. I don't know if it's, you know, trajectory modeling or something of actually looking at, you know, where the places are that are experiencing the largest changes, and where their, you know, moisture is coming from, and what are the temperature trends at those locations would be a much more robust way to handle that, for sure.
We have a comment from Allegra. Allegra, is there any chance you'd like to say hi?
Sure. I was just saying, like, I have the runs to look at exactly that thing. I just haven't looked at it. We did it. My old postdoc, Jesse Nussbaumer, we did a paper for Greenland, but we just haven't looked at the same thing for Antarctica. But we should.
Always more to do, right?
There's just not enough hands.
Laurie, is there any chance you'd like to
Oh,
Yeah,
since
hi,
I,
Brooke. Oh,
oh,
go ahead,
I-
Allegra.
I'm sorry, I had one tiny thing. Did you already say, there's that Grace paper that has Antarctica and a nice trend line. Did you already compare what your result was with that one? And I don't remember the Grace paper to have quite so much of an oscillation to it, but maybe that's just a function of their method.
Yeah, and it's a good point. And so this paper was led by Ben Smith, and I think our numbers were a little bit less negative than Grace, but there is actually a pretty strong seasonal signal to Grace. There is a strong precipitation seasonality that gets that manifests in the Grace data. So it actually is there is pretty good seasonality that you can see in Grace. That answers your question.
Thanks.
Brooke, this is Laurie. Can you go back 2 or 3 slides to your time series of SMB and FAC?
This one?
Yeah, that one. So this is constrained to this is the residual, and this is constrained to start and end at 0. Is that correct?
That's correct. That was by choice, yeah.
Right. So that assumes that's all relative to steady state during that 40-year period.
Yep.
Do you have any sense of trends through that 40-year period?
Yeah, that's a great point. I didn't touch on this, but by design, because everything about the surface height change has to be against basically a steady state, as Lori just said. And so you have to tell, in your model setup, you have to decide what is the steady state climate that I'm going to then that I'm going to spin my Fern model up from, and then let it evolve into the future. And so for Antarctica, we chose to just say that the full 40 years from 1980 to through the end of 2019 is representative of the long-term mean climate. And so what that means is that we spun it up with the 1980 to 2019 mean climate, just repeating it over and over again. And then what that also means is exactly what you said, is that the height has to start at 0 and end at 0 in December 31st of 2019. I looked at, and we chose this because trends integrated over the whole ice sheet are insignificant in snow accumulation and in temperatures over this time period. And so we didn't feel that we could necessarily isolate a specific window. And I think my argument would be the longer your sort of reference climate or your long-term climate, the better, because then it can just start to freely evolve from that reference climate, if that makes sense. So I think what I also showed, and what I eventually want to do, is I obviously showed you there's been these trends in snow accumulation. So what I just said is in absence, like without considering that at all. But in reality, the Antarctica is still responding to those longer term changes in snowfall and temperature that are not included in this model. And so they could be imparting a different height change signal that we see in ICET 2, but that the model is not accounting for. And so where I want to go next is really starting to look at, can we take the work that I showed of reconstructing snow accumulation, put it into the Fern model, and see how big that signal becomes in, say, modern day, and what that means. Maybe it becomes negligible at this point, but I don't think anyone really knows necessarily at this point.
Okay, quick follow-up question, maybe easier. The dip at going into year 2000 in SMB, does that make sense? I mean, what's the basic driver for that dip? I mean,
Oh,
it's coming out of the model, but it's coming out of the SMB model, but it's associated with SAM or something else.
Oh yeah, I don't know what the drivers are. I just know that, you know, this is from basically there's these like, yeah, seasonality in the SMB, and SMB for Antarctica is like 99% snow accumulation. So this is all just a snow accumulation signal, but I haven't looked on to sort of finer timescales of what is actually driving it. I just know that there is a strong seasonality in snowfall where winter months receive significantly more accumulation than in summer months. So, but beyond that, I can't tell you what's actually why there's more in the winter and less in the summer.
Okay, thanks.
Were you talking about the multi-decadal signal there? Sorry.
Yeah, that's what I'm looking at. So I'm just, I mean, you could follow this along and maybe discover that it was mostly changing in West Antarctica near the coast, or a large integration area up on the plateau, or
right. I see what you mean. You didn't mean like the actual like dip in 2000. You meant why is it at a low in the, say, the 2000?
Yeah, sorry, I wasn't clear. It's there's the long-term trends that I'm within that 40-year period. The apparent cyclicity that it's a little bit disturbing to me that it's very close to the length of the record that you're working with.
Right. No, it's a fair point, and it's something that I wish we had like 200 years of data so we wouldn't have to worry about these things. But it's actually a really interesting thought that I never had, is like, what is the difference about, say, the 90s than the 2010s, so to speak. So yeah, I don't have a great answer for you, except we just need more years of data so that we don't have these weird challenges. But
okie doke. I'm afraid we're going to have to close off the stream soon, as some of us have another meeting. And we have a group meeting to go to. Thanks very much, Brooke, again. Do we have any perhaps final questions, comments before we have to close out?
Yeah, I had a quick question. I was wondering, I'm interested in the Fern air content variability, and I was wondering if there's been any a comparison with in situ data of how the model performs, and how, if you can say anything about how reliable it is regionally at different places around Antarctica.
yeah, that's a great question. And I think that's one of the, you know, what Lori brought up, and then also what you're bringing up is definitely the tricky part is, how do we measure these processes? How do we measure for an air content, and not even just for an air content, but its variability through time? And that's really tricky. And there are a few